What you are looking at isn't just geometry. It is a simplified version of how isolated corners of the world work. The world around us is causal. Things don't just happen. Things happen because something nudged them first. Every raindrop, grade, TikTok trend, or traffic jam is the result of an invisible arrow in some causal map pushing forward in time. In the bottom left corner is one of the simplest possible causal maps, indicating that X causes Y somehow, without saying anything more about the nature of that causal relationship, and the U variables are stand-ins for other factors causing X and Y. In the top left is a fully fleshed out version of this causal map, detailing exactly how X causes Y. This is done on the line which reads Y equals 0.75x plus uy. When one variable causes another one in the real world, almost invariably, they leave a footprint in the data, in the form of dependence between the two variables. That colorful mountain you see on the screen is the footprint that this particular causal map would leave on the data. It is the joint distribution of the two variables x and y, and in this particular case, it would be in the shape of a bivariate normal distribution with a correlation of 0.75. So if we observe two variables to be strongly dependent or associated, can we conclude that they are actually causally related? Unfortunately, things are not that simple, because two variables may be dependent without either one causing the other. For now, I will rely on your intuitive understanding of what it means for one variable to cause another, and for now you can just think of dependence as correlation, although dependence is a much broader concept than correlation. But this should be enough for us to make a connection with that phrase you have heard probably ever since 5th grade, which says that correlation does not imply causation. In studying statistical inference, you will find that we often start by assuming some joint distribution over the variables of interest, and we make assumptions about how that particular sample that we have was obtained from the joint distribution. Here's a visualization of the sampling process. The mountain-like structure is the joint distribution, and next to it is the sample. Even though we usually work with only one sample of data, we should be able to imagine that due to randomness, we could have possibly drawn a different sample. Here I depict 3 samples drawn from the same joint distribution. And here's the central idea of this video. There are 2 distinct universes out there: the causal universe inhabited by causal models, and the dependence universe inhabited by joint distributions and its characteristics. Both of these universes are unseen and are theoretical. All we see is the sample of observations that we have. With a large enough sample, we can start to get a glimpse of certain aspects of the otherwise hidden dependence universe. A glimpse at the causal universe will come at a much higher cost, and it will require not only a large sample but also a deep understanding of the subject matter. This is why causal inference is generally done by people who are subject matter experts in the question at hand. For example, sociologists will study causal questions in sociology, economists in economics, and political scientists in political science. Data science is like a detective game that you play using the sample of data that you have to deduce something of interest about either the dependence universe or the causal universe. We can equivalently think of our sample as having been generated by a causal model, or as sampled from the joint distribution induced by this causal model. Much of what we are after in data science can be described in terms of these three distinct entities: the causal model, the joint distribution induced by the causal model, and the sample. In fact, let's use these to discuss the different courses one would typically study in their data science educational journey. Probability is typically the first course one would take. Probability is the mathematical language used to reason in the presence of uncertainty. There are typically two types of questions in probability. One, when we know a certain distribution in the dependence universe and we are asked to induce something about what a sample of data from this distribution will look like. And two, when we know a few things about the dependence universe and we may not even have any sample of data, but we want to use what we know about the dependence universe to learn something else in the dependence universe. For example, we might know the probability distribution of a random variable x and a random variable y, and we may want to understand what the distribution of x over y would look like. After studying probability, one typically would go on to study statistical inference. Statistical inference is mostly about using the sample of data in hand to learn something about the dependence universe. If the statistician is himself or herself performing an experiment and gathering the data, then he or she may be able to answer some causal questions as well. In this experimental scenario, statistical inference becomes concerned with causal inference, and I will discuss that under causal inference. Machine learning is largely focused on modeling statistical associations and delivering accurate predictions for future data. While its roots lie in statistics, machine learning emphasizes risk minimization and scalability rather than the formal estimation of fixed population parameters. But at the end of the day, machine learning can usefully be thought of as a type of statistical inference, and just as in statistical inference, in machine learning we will have a sample of data in hand and our task will be to use it to infer something of interest about the dependence universe. Finally, causal inference is about using the sample of data we have to learn usually only about one single variable at a time in the causal universe. For example, we will look at a super important model called regression. After careful thinking and analysis, we might run a regression of one variable on 15 other ones, and we would include 14 of those 15 variables with the only goal of helping us correctly identify the coefficient on the 15th variable. In other words, those 14 variables would be included out of necessity, and only because they help us have a glimpse at the causal effect of the 15th variable, the variable of interest. This will be explained in due time, but I do want to make a distinction early on between causal inference and causal discovery. Causal discovery is concerned with using the sample of data to deduce the entire causal mechanism that has generated the data, whether or not we have data on all the variables that were part of the generative causal mechanism. In causal inference, our scope will be very narrow. We will want to learn something about only one variable or coefficient at a time, whereas in causal discovery, our scope will be as large as it gets, as we will seek to learn about the entire causal mechanism that generated the data. Now that we have built the shelves in our minds for the two different universes and the sample, let's get a little more practice with each of these. For example, suppose we have a sample of 10 observations on two random variables. We calculate their sample correlation coefficient to be 0.396, and we plot them on a coordinate axis and draw a least squares line. Let us have a look at the eye-catching sight of what is called a standard bivariate normal distribution, or a bivariate normal distribution with a correlation of 0. If two random variables each had the standard normal distribution and were independent, this is what their joint distribution would look like. And in the bottom left, let's bring on another bivariate normal distribution, but this time one in which the two variables are correlated with a correlation coefficient of 0.75. Now here's the question. When I sample the 10 observations, I sample them from one of these two joint distributions. Was it the top left one or the bottom left one? In other words, did the sample come from the bivariate normal with a correlation of 0 or from the one with a correlation of 0.75? With a sample of only 10 observations, it is difficult to tell. But if we were to sample more observations, at some point it becomes crystal clear that the sample came from the bottom distribution, the one in which the two variables have a correlation coefficient of 0.75. Okay, so we've had a little bit of practice with using the sample of observations to infer something of interest in the dependence world. Now suppose that we are certain that our sample came from this bivariate normal distribution with a correlation of 0.75, and we wanted to figure out the causal graph or causal model that induced this joint distribution in our two variables. Suppose that, based on our knowledge of the subject matter, we have narrowed the candidate list of causal graphs to the three that you see on the screen. Let's look at these one at a time. In the top one, x causes y. In the middle one, a variable called z causes both x and y, but crucially, neither x causes y nor does y cause x, which you can tell by the fact that there is no arrow between x and y. And finally, in the bottom graph, y causes x. The causal graphs on the left tell us which variables cause which, but do not say anything more about the nature of these causal relationships. We will later say that these relationships are specified non-parametrically. The point is that infinitely many different models are consistent with each of these three causal graphs. To the right of these causal graphs, I fully spell out a particular causal model for each of the three causal graphs. Remember that we said that we equivalently can think of our sample as having been generated directly by a causal model or as having been sampled from the joint distribution induced by a causal model. We've already seen the latter scenario, where we sampled the observations from the joint distribution. Now let's have a look at the former scenario in which the observations will be generated directly by a causal model. If we take the first causal model as an example, notice what it stipulates. It assumes that ux has a normal distribution with a mean of 0 and variance of 1. uy has a normal distribution with a mean of 0 and variance of 1 minus 0.75 squared. X and ux are identical, and y equals 0.75x plus uy. In order to sample a vector xy, or in other words, in order for us to sample a value for the pair xy with this causal model, we would start by randomly sampling a value for ux and uy from their respective distributions. X being identical to ux, we just set x equals to the value of ux, which is 0.3 in this case. And then we compute y by plugging the value of x in the expression 0.75x plus uy, and we are done. We get the random vector 0.3 and 0.925. This random vector is the first observation we've generated with our causal model. We can then repeat this process, and as we have a larger sample, we can explore what sort of joint distribution this causal model induces on the variables x and y. as this video suggests, it turns out that these three very different causal models would induce the exact same joint distribution on the variables x and y. To be exact, each of these three causal models will induce a bivariate normal distribution with a correlation of 0.75 in variables x and y. This example should serve as a cautionary tale that the same joint distribution could be consistent with many different causal models. So I hope that as you begin your educational journey in data science, you build this structure in your mind with these two universes, the causal universe and the dependence universe, and the sample. As you solve problem after problem and build model after model, if you take a moment to contextualize it in terms of these universes and the sample, it should help you avoid the traps that generations of data scientists before you have fallen into, at times mistaking the causal universe for the dependence universe and vice versa. I hope that you find this video helpful, and I hope that you enjoy your journey into data science.